All right, so let's take a look at this. You know, this is just one of those things that this is a kind of a representative question that you might see on a quiz or exam. And so as I go through this, it's real easy to say, yep, that makes sense, that makes sense, that makes sense. But if you can't get started on this problem before I work on it, then you're not ready for that quiz or exam. So make sure that you're honest with yourself as you go through this. If you can't get them started, then you need to prep more. Right? You need to go through this and then leave this class and see if you can get started on that next problem. And if you can't, come and see me. Right? Come visit the office hours or schedule some other time or do whatever it takes because you're not ready for that quiz or exam coming up yet. All right, so we have this region. It represents a thin metal plate. We're given a density. The density is grams per square meter. So what do I need to multiply this thing to get grams? Square meters, right? Some sort of area piece. So can I take density times area, and that should give me my grams? That should give me my mass? Not really, not through this whole region here. I can't just find this area as an integral and then take that number value and times it by this thing. That won't work. One, because then I would get 10 times this thing, which isn't a number. I want to find the total mass. I want to find some number of grams. But I also can't do that because it's different. The mass is different here than it is here. It's more dense here, less dense here. So I can't just say density times the whole area because the density is changing throughout that stuff. So what I have to do is I have to look at a thin slice. I say if I look at one little piece here, if I cut that slice thin enough, the density is constant in that little slice. So if I just try to find the mass of just the slice, because it's thin, because the density is constant there, it really is just density times area. It's just my density times the area of that slice. And what is the area of that slice? Well, it's just the height of the slice. There's the height. That's this distance. That's x squared plus 1 times the thickness. What's the thickness? Delta x. So that is the mass in one little slice. Find the total mass. I am just adding all those slices up. The density is the square root of x cubed plus 3x times my x squared plus 1 times the height times the thickness. Adding them all up from x equals 0 to x equals 1. That's the setup. Now I said in this case we can actually do the integral. Yikes. How do we do this integral? Substitution. It's one of the first ones I check for. I check for some kind of basic simplifications. If I don't see anything jump out at me, I look for substitution first. I mean, it's a product, which might make you tempted to start integration by parts. And who knows, that might even work, but it's going to be longer and it's going to be harder. So always check for substitution first. Here I'm going to let u equal x cubed plus 3x. The derivative will then be 3x squared plus 3, which looks like 3 times x squared plus 1. There's my factor. I'm solving this thing for dx. I'll get 1 over 3 times x squared plus 1 times du. And I'm plugging all that stuff into my integral. It's going to be the square root of u times x squared plus 1 times 1 over 3 times x squared plus 1 dx. I'm sorry, du. All my x's are going to cancel out, which makes me pretty happy. And I certainly could do this and do the integral and switch back to x's, but I'm going to do this one a little differently. I'm just going to integrate and evaluate with respect to u. If I'm going to do that, though, I have to change my limits of integration from x equals 0 and x equals 1 to something meaningful in u. So in this case, I'm not just going to find the antiderivative and go back to x's. I'm going to actually change my limits over. This is another way we can do definite integrals with substitution. So I have to say when x equals 0, what would the associated u value be? 0. I just plug them into my equation that relates u to x. When x is equal to 1, u is equal to 4, right? 1 cubed plus 3 times 1. So now I'm going to do the integral. Looks like I have 1/3 times the integral of u to the 1/2. Integrating u to the 1/2 gets me u to the 3/2 divided by 3/2 or times 2/3. Evaluated from 0 to 4. I'm going to get 2/9, and I'm going to get 4 raised to the 3/2 power minus 0 raised to the 3/2 power. 0 raised to the 3/2 power is 0. 4 raised to the 3/2 power. Well, that's like taking the square root and then cubing it. So if I take the square root of 4, I get 2. If I cube it, I get 8. Altogether, I'm going to end up with 16/9. 16/9 grams. That's the mass of this plate. All right, any questions about that one? Brings a lot of ideas together. It's taking a big problem, cutting it into a small piece, to set up the integral, and then actually evaluating a challenging integral via substitution. Any questions from the warm-up? Okay. All right, plan for today. First thing I have up here is a little admin note. I got an email the other day from the Learning Center. They have opened up for Track B. They have hours of noon to 4 p.m. Monday through Thursday. So they're down on the second floor. The math lab, which is on this floor, Fisher 331, has been opened and will remain open from 9 a.m. to 12:30 p.m. And they're there to help you with the mathematical stuff. But they can also help you with the calculus stuff too. So feel free to kind of treat them like a learning center as well. So between the two of us, we have kind of covered from about 9 to 4. Monday through Thursday. All right, our plan for today is to go over what you should have watched in that partial fractions video. So we're going to go over that pretty quickly, do a couple example problems, because you read the section and watched the video. After that, we're going to extend those ideas to do some harder problems, reinforce when to use it, and also bring in the next topic of trig substitution. Any questions before we get started? Any questions about the reading or the video? The math lab should be open from 9 a.m. to 12:30 p.m. Sometimes it's open to 1 p.m. on certain days, and that's also Monday through Thursday. And if you need help on Friday, then you can stop by my office. I'll help you with the lab too. So. Other questions? All right, then I want you to take out a clean sheet of paper. Put your notes away, clean sheet of paper. We're going to do a preparation quiz on partial fractions. Make sure you have a name on it. All notes away. All right, preparation quiz. We have, can I get all four here? Let me read through the directions and I'll show you all four of them. All I want you to do is give the appropriate form of the decomposition for these rational functions. Partial fractions is all about taking a fraction, a ratio of polynomials, and breaking it down into the sum of easier to work with fractions. And there's a form of the decomposition. I want you to just write the form. It's going to have coefficients, A's and B's and C's and stuff. You don't have to find the coefficients or do anything more complicated. Just write the form that the decomposition will have. Okay. And I want you to do that for these 4 fractions.
So we can't have A's, B's?
You can. I expect you to have A's and B's and C's. Right? we take something like this and we write it as A over something plus B over something, maybe plus C over something, maybe plus something else weirder, right? That's all the stuff from the video and from the section. So I'm saying write out what that decomposition is. You don't have to solve for the coefficients, but write out the form that you would use. I apologize for the yellow. Another minute or so. Remember, you're just writing the form, not doing any simplification or any solving for constants. Just rewriting the form. Make sure your name's on them. pass into this aisle. All right. I have them all. All right, so these pre-preparation quizzes here are not designed to be challenging. All right, so if you read this section, you watched the video, and you have problems with that, then let me know. Send me an email saying that was a little challenging. I put in the time, I really did. And that's not what I want them to be. I want them to be free points as long as you prepared for the section. Doing that work before coming to class, it makes the class go smoother, helps you not fall behind the lecture, and once you start falling behind, everything just kind of steamrolls. So it's really important to prepare for class as you come forward. So,
Third one?
yep, I'm going to do them all real quick here just so we can see them all. All it is about breaking partial fraction, just like take this complicated fraction, and we can always break it into the sum of smaller fractions where each of these factors are in the denominator. In this case, because these are just distinct linear factors, it's just a plus the first one plus b times the second one. The next one is a repeated factor. So how do we deal with repeated factors? We do a over x minus 2 plus b over x minus 2 squared plus c over x minus 2 cubed. That's just the form that we have to be able to write out. The second one is an irreducible quadratic. I can't factor that x squared plus 1 into individual pieces. And if you think about what the roots would be, the roots would be complex. It would be plus or minus I. It doesn't factor into these nice little form. So we have a special form for that. We write ax plus b over x squared plus 1. In this case, it's kind of a cheesy example because guess what a and b are? 2 and 1. Right? We'll talk more about that later. But in general, that's how you deal with an irreducible quadratic bottom. And the last one. Yep. Can you complete the square on this one? What would you get when you complete the square? I mean, the thing is normally when you complete the square, you have an x term, right? And you're manipulating the constant to make it right so that you get this thing squared plus or minus some constant. In this case, you have to add an x term, right? You have to add like plus 2x. Okay. So you have to add and subtract plus or minus 2x, which would give you something squared plus or minus 2x. And that would make this problem much harder. It's one of those things we just have to recognize the irreducible quadratics and write that associated form. And then the last one we factor first. This is the same thing as this, x plus 1, x minus 1. And therefore we really treat it just like the first problem. It's just a over x plus 1 plus b over x minus 1. Any questions about those? Once again, that's the first step in this process. Now, there's a lot of details in the computation. There's a lot of harder problems. And those are the things I want to spend class time on. Because otherwise I can get you through this basic stuff by just reading the book to you. But then we don't have time to get into the harder problems. And then when you see those harder problems on quizzes, exams, it's like, whoa, these are blowing my mind, right? So we need to get through the basics on your own so we can talk about the harder things, so we can review this stuff or answer questions about this stuff instead. All right, so that's the preparation quiz. Now let's quickly go over kind of the video overview. What do we talk about in the video? We have a new technique. It's integration by partial fractions. So there's all these kind of standard things. When are we going to use this technique? How do we identify an integral that we're going to use this technique on? Then, of course, how do we do it? And then the tricks, the tips, the problems that we're going to encounter as we actually apply this to different integrals. So we start off and say, when are we using this thing? Partial fractions is an algebraic trick. It's an identity. really has nothing to do with calculus. It just says that if we're integrating some tough function, some tough rational function, which is the ratio of polynomials, then we can take this thing and break it into separate fractions, and thus separate integrals, because the integral of the sum is the sum of the integrals. And these individual pieces are going to be much easier to integrate than the original thing. That's the whole game. Of course, the first thing to know is how do we break them up? So what I like to do is kind of memorize one problem. This is the one problem that has all the forms. There's three things we've got to look out for. Distinct linear pieces, x minus 1, x minus 2, where there's just one of them. And these just come out on their own. X minus 1 in the denominator and some constant on top. And then there's the repeated forms like we saw on the preliminary thing. If we have a repeated case, x minus 2 raised to some power, we have to have each individual piece for every power here. We have to have x minus 2, x minus 2 squared, x minus 2 cubed, x minus 2 to the fourth. We have to have one for each of those. But in the numerator is just a constant for each. And then, of course, the irreducible quadratic. For the irreducible quadratic, we're putting a linear term in the numerator. It's some constant times x plus some constant. And this is actually a theorem from algebra. We're just applying it here. So it's really kind of a mechanical process. You see this one, and you're going to break it into something that looks like this. And all those coefficients, a, b, c, d, e, f, g, they're just numbers. Of course, the tricky part of this process then is finding out what those numbers are. I'm going to go for it here, or do I want to go for that later? So let's practice one here. So we're going to do this one. Once again, the whole idea is to just take this fraction, this 2x, x plus 1, and x minus 2, and says, I know I can rewrite it like this. I know there exists some a and some b that make this statement a true statement. I just got to find out what a and b are. And why? What's the purpose of doing this? Well, once I find out what a and b are, then I can just rewrite my integral. It will look like this integral now. And I'm happy about that, because those individually are pretty easy integrals. It's just a times the natural log of the absolute value of x plus 1 plus b times the natural log of the absolute value of x minus 2. So as long as I can write it in this form, the integration becomes easy after that. That's the goal here. So it's like I can almost write out the solution right away, and I just got to figure out what a and b are. So to find out a and b, we have this algebraic equation. And this is what we're going to do. The first thing we're going to do is we're going to multiply the whole thing, multiply through the whole equation. Remember, I can multiply through the whole equation by stuff. I can multiply through the whole equation by x plus 1, x minus 2. That denominator, the original denominator. When I multiply through the whole equation by that, on the left-hand side, what do I get? 2x. On the right-hand side, as I multiply each of these pieces by that, well, for the first one, the x plus 1s will cancel out, and I'll get x minus 2. For the second one, the x minus 2s will cancel out, and I'll get x plus 1. So I'll get to this form. And now from this point, we have two different choices for solving this. Kind of a formal process, and then a shortcut down and dirty process. Okay? So first we're going to go through the formal process. The formal process says blow this thing up, right? Distribute A, distribute to B, and then regroup it to look like a polynomial. Right? I have x terms, I have constant terms. If I reorganize this, I should get a first degree polynomial. I should get something times x plus some constant. And once I regroup it like that, I can compare it to this polynomial. This is also a first degree polynomial. It's 2 times x plus 0. For two polynomials to be equal, their coefficients have to be equal. Whatever the coefficient to the x term is over here, it has to equal the coefficient of the x term over here. So, we're going to blow up that right-hand side. ax minus 2 plus bx plus 1. We're going to regroup. We're going to gather the x terms to get a plus b times x. Oops, sorry, that's 2a and b. Thank you. Then distribute my a, distribute my b. I group my x terms, and then what I'm left with is minus 2a plus b. This is all equal to 2x. And now I say, okay, if these two polynomials are equal, then the coefficients to the x term have to be the same. Here my coefficient of the x term is 2. On the other side, the coefficient of the x term is a plus b. If these two polynomials are equal, their constant values have to be the same. On the left-hand side, the constant is 0. On the right-hand side, it's negative 2a plus b. I've generated two equations and two unknowns. Now I can solve these two equations and two unknowns. I'll start with the right side first. I'll move the 2a to the other side. That gives me b is equal to 2a. That's a value for b. And I'll just plug in that value for b to the other equation. I get 2 is equal to a plus 2a. I get 3a equals 2. So a must be equal to 2/3. I'm sorry? Over here?
The 2a is subtracting, not added.
So I had negative 2a, I added two equal sides to get this expression, and then I just plugged in what's b equal to, b is equal to 2a. Okay. It's good. Make sure you get into those little questions you have along the way. Make sure you get them answered, because otherwise they're like a splinter in the brain, right? They make you miss things as we go on. So make sure you get them answered.
Can you explain where you got that 2a on the left-hand side?
This one?
Yeah.
So I have these two equations, right?
Mm-hmm.
Okay, so first I solve this one to get an expression. This expression tells me that b is equal to 2a. So I'm just replacing the b with the 2a. Okay. That lets me solve for a. But if a is 2/3, I have a relationship now to find b. If a is 2/3, what's b? B is equal to 4/3. And then I know my solution. My solution now is 2/3 natural log of x plus 1 plus 4/3 natural log of x minus 2 plus some constant. All right. That's one process. That's like the formal process to find a and b. Now here's the shortcut process. That equation that we've written up here, this equation should always be true. It's an identity. It should always be true. It should be true no matter what x value we use. For any value of x, that identity should hold. So I'm just going to look at some specific x values. That equation should be true when x equals 2, for instance. But if x equals 2, then the equation actually looks like, well, if I plug in x equals 2, I get 4 equals a times 0 plus 3 times b. So b is equal to 4/3. That equation should be true for any value of x, even x equals -1. If x equals -1, then the equation looks like -2. A times -1 minus 2 is -3 plus b times 0. So So a is equal to 2/3. What's that?
Just find a 0.
Yep, you just choose x to be those zeroing values and then see the resulting equation. It's choosing the x's that eliminate one of the variable, or one of the parameters, I should say. Now, much easier, right? Woohoo! Feel free to do it that way. Unfortunately, as the problems get bigger, that tends to be harder to do. I mean, what happens if this was a big problem? What happens if it was this problem? Yikes. I mean, we have 1, 2, 3, 4, 5, 6, 7 constants to find. Now, we can blow this thing up. If we think about what the degree of this thing is, I got x squared, I'm going to have x to the 4th. When I blow this up, I'll have x over here. It's a 7th degree polynomial. So when I relate the coefficients, I will get 7 equations, and I have 7 parameters to find. So I should be able to do that. But it's hard. It's linear algebra. 7 equations, 7 unknowns. It's a matrix equation. And that's how you really would find that thing. And some of them, it's going to be very hard or impossible to say, well, what if x is this? And eliminate them properly. You could probably get through most of them if you mapped it out just right and figured it out. But really, it's a linear algebra problem. Now, am I going to have you do that on an exam? No, because it will take you the whole hour and a half to do the algebra to find the coefficients. And that's not what I want to test on. But I certainly might write out the decomposition for this. Right? Evaluate these integrals without finding the coefficients. Questions like that allow me to test if you can do it or not, kind of avoiding the long algebra. And when we think of problems like this, though, and we said, it'd be hard to find the coefficients, and it'd be a linear algebra problem. But even if we could find the coefficients, can we do the integrals? What's the first integral? I mean, the real problem looks like this. Find the integral of this thing. And we say, great, we can do the decomposition, so now we just get the integral of all these. What's the integral of the first one? A times natural log of x minus 1. Okay, I can do that for this one too. B times the natural log of x minus 2. Ooh, what about this one? No, natural log is for 1 over x, not for 1 over x squared. And this is 1 over something squared. Which is essentially just, if we did a little substitution, let u equal x minus 2, it would look like 1 over u squared, which is really just power rule. So all these things are going to look like substitution and power rule. Power rule. So those aren't too bad. We definitely have ways to deal with that. And then we get this last ugly thing, right? Ugh. I'm not going to be able to use substitution necessarily here unless f and g are just right. If f was 2 and g was, well, nothing, I won't be able to do it. Can't do it. But what I can do is break this up into 2 integrals. I can break it into this one plus this one. Getting closer. Can I do this integral? Again, that's also a substitution. If I take the derivative of x squared plus 1, it's going to look something like x. X is a factor. I can do substitution here. How about this one, though? Can't do substitution here. I don't have that x factor that I need. I can't factor the denominator. I can't use partial fractions. I'd be going backwards. Right? I don't know how to do this one. To do this one, in fact, we need another technique. We need trig substitution. So that leads us into that other section on trig substitution. Trig substitution is a tool that lets us deal with ugly quadratics. 1 over x squared plus 1, that's a quadratic piece. The square root of x squared plus 1, or 1 minus x squared, or 16 minus x squared. All those quadratic things we're going to be able to do with trig substitution. So that's a new technique. So when do we use it? Well, we use it when we run into these ugly quadratics. We're doing the square root of a quadratic. We're in the denominator. Here's a couple examples where we might encounter that. And there's going to be a mechanical process that we're going to follow. But as with all these techniques, it's almost more important if you understand the concept behind the mechanics. What's the goal? What are we trying to do with the mechanical process? In this process, our goal is to turn this thing, number squared plus x squared, or number squared minus x squared, into just one thing squared. Because what makes it difficult is we have the sum of squares. If it was just one thing squared, it's much easier for us to handle. To do that, though, we're going to need some trig. We're going to need to put a trig thing in here. So that's the big picture that I want you to see before we go into the details. Now, some of the details here. Why is this going to work? Well, let's show an example where it works. And your book does this really well. So this is pretty much right from the book, this example piece. Because I really like how they explained this before they went into the integration. If you have something that looks like some number squared minus x squared, and if we make a substitution, if we let x equal a times the sine of theta, for instance, and we just see what happens when we plug that in. We get a squared minus x squared is equal to a squared minus, and I take my x and I square it. What do I get? What happens when I square this thing? A squared sine squared theta. And I can factor out a common a squared. And now I say, wait a second, 1 minus sine squared theta, I know what that is. That is cosine squared thing. I have taken that sum or difference and turned it now into just one thing squared. And that's the value. We were able to do that because we have this thing, sine squared theta plus cosine squared theta equals 1. So that means cosine squared theta is equal to 1 minus sine squared theta. We're making use of that tool now. But does that always work? What if I didn't have a squared minus x squared? What if I had a squared plus x squared? What if I had x squared minus a squared? Can I handle these with that substitution of sign?
Where do you get the negative, or 1 negative squared?
This thing?
Yeah.
I factored the a squared out.
Oh.
Right, so it's kind of easier to see if you go from here to here.
Yeah.
And say they're equal. If I distribute that a squared, I get a
Yeah.
squared minus a squared sine squared. Good.
I just didn't.
Yep. A good question. It's one of those little steps along the way. That just ask, answer real quick, and you're right back. Don't let any of those little things, like I said, be splinters in the brain.
Substitute tangent functions or get to tangent functions.
Why tangent?
Because tangent squared theta minus 1 is equal to secant squared theta.
Let's check it. All right, we used this one because we had number squared minus sine squared. Now we have that other relationship here. If I just take that whole equation that I'm using right now, or maybe this one even, and I divide it by cosine squared. We did this before, right? If I divide it by cosine squared, I get tangent squared theta plus 1 equals secant squared theta. I like that. That should handle this piece. Right? I mean, here I have x squared. If I just switch these two, 1 squared plus tangent squared. Number squared plus tangent squared equals one thing squared. So that should handle this case. And then with this case, where I have something squared minus, I could subtract 1 here and use that. That would have something squared minus number squared. Or I could just kind of rewrite this as negative a squared minus x squared. And I'm back to my original case. Either should be valid. Some will be more or less useful as we go to a specific integral. But that's the concept. Your book will say, there are some forms. If your integral matches this form, then use this substitution. It's not magic. Right? It's not a formula sheet that you have to memorize. It's saying, okay, I got this and I want to turn it into one thing. And I know that this identity is true. And how can I leverage that? Right? Well, if this thing was tangent squared, I'd be in business. So I want to replace this with a tangent. Replace x with a tangent.
Did you factor out that negative there, or did you just multiply the whole thing by a negative?
I multiplied the whole thing by a negative, right? So
Does that turn the 1 into negative 1?
what did I do here? I just factored out the negative, right? Yep, I just factored out a negative. So I didn't multiply through by anything, so I didn't change the right-hand side at all. And if I distributed that negative, I should get negative a squared plus x squared. And if I just switch the order, so just rewriting it in a different form, factoring it out. Good questions. Other questions? Now the other important thing to look at here is that this is not the same substitution we did before. This is fundamentally different. And so I want to make sure we're strong on why it's fundamentally different. So I got this big giant table here. I'm going to scroll down a little bit so you can see all the pieces. Those are all the pieces. And I'll scroll up a little bit so we can actually see the integrals. On the right-hand side, I have the steps for doing regular substitution, U-Substitution. We find our inside function. We let u equal that inside function. We take the derivative and we solve for dx. We plug all that stuff back in for our integral, put all the u values in, and we organize and integrate it. And hopefully we've got to an easier integral. And we put our x values back in. So I have an integral up here that we can do that on. This one. My inside function would be u equals 4 minus x squared. I take the derivative. You don't necessarily have to write this stuff down here. The derivative would be negative 2x. I'd solve for dx, which is following my steps. It would be a negative 1 over 2x du. And then I substitute in my u values. I get the integral of x over the square root of u. And then I get negative 1 over 2 dx du. My x's cancel. I finish out the rest of the process. But the idea here is that we look at this integral and say, oh man, all this stuff in here is tough. I don't know how to deal with all this stuff. So I'm going to get rid of all the hard stuff by replacing it with u. This is a little different. We're not grabbing some big ugly chunk and getting rid of it. Rather, we're changing what x is. We're changing what x is so that this thing will simplify by itself. It's a little bit different kind of substitution. So we have similar but different steps. Our first step is to identify the form that we're in, to tell us what substitution we want. In this case, what kind of substitution do I want? So here, am I in this form? Am I in this form? Here I have number squared minus x squared. So what was the substitution that fit with this thing? Was it sine or was it tangent? Sine in this case. It's easy to forget. It's easy to get them confused. So just remind yourself, oh yeah, I know that sine squared x plus cosine squared x equals 1. Okay, cosine squared x equals 1 minus sine squared x. Okay, I got it. Right? It's number minus something squared, that's the sine substitution. Okay. Now in this case, that a squared is related to this thing. If I multiply this thing all the way through, okay. So this is my a squared piece. And it's the 1 there. So my substitution is going to be x equal a sine of theta, because I'm going to square it in a little bit. So in this case, we have 2 sine of theta. Okay. So So I've identified the form, whether it's a sine substitution or a tangent substitution, by relating it to that proper trig identity. Now I let x equal that thing. And the rest is just kind of process. The big step is getting that first substitution. Now we're going to do the same thing. We're going to take the derivative and solve for dx. Just like we did before. What is the derivative of x with respect to theta? X equals 2 sine theta. What's the derivative of x with respect to theta? 2 cosine of theta. And if I wanted to solve that for dx, I get 2 cosine of theta d theta. And then just like before, I'm going to plug all this stuff into my integral. And here I'm not expecting any cancellation, so I'm really just going to replace everything. All the x I'm going to replace with my trig function, and I'm going to replace the dx piece. So my integral turns into the integral of 1 over the square root of 4 minus x squared. Well, 2 sine theta squared is 4 sine squared theta. I replace the dx by what it's equal to. It's equal to 2 cosine of theta d theta. I'm just plugging stuff in. Now, unlike U-Substitution, my integral does not look any easier. In fact, I would say it looks much harder. Okay? U-Substitution covers up all that difficulty. This thing, it's like, oh boy, now it looks really ugly. Like the simplification is hidden here. It's hidden right here, though. If I factor out that 4, this thing looks like 4 times 1 minus sine squared theta. What is 1 minus sine squared theta? Cosine squared. So really I'm taking the square root of 4 cosine squared. So I have my 2 cosine theta. The square root of 4 cosine squared is 2 cosine theta. So it really does simplify. I'm just integrating 1. What is the integral of 1 with respect to theta? Theta. Yep, theta. So the solution is theta. Sort of. And now we got to get back our x's. How do I get back my x's? If the solution is theta, what's my solution in terms of x? How do I find that?
X over a arc sine.
Yeah, I go back to this thing. X equals 2 sine theta. I solve that thing for theta. So I would divide by 2 to get x over 2 equals sine theta. And then to solve for theta, I would take the arc sine of both sides. So my solution is the arc sine of x over 2. And of course, plus constant. Right, so to find that solution, to find what is theta equal to, I'm using this thing. I'm using x equals 2 sine theta, the relationship between x and theta, and I am solving it for theta. Any questions about that?
How did you get back to the
So let me just grab this over here. I started with this substitution, right? So if I want to solve that for theta, I divide both sides by 2. And I take the arc sine of both sides. So then I would get arc sine of x over 2 equals theta. Okay? Thank you. I was kind of pointing and talking, but I wasn't ready. So thanks. All right, I'll drink some coffee. Identifying a process that will work for you. Identify that key steps. Yep.
So the solution to your trig substitution is not just theta. At the end, would you want to solve for, say, if it were 2 theta?
If it was 2 theta, yeah, then I would figure out what theta was, and it'd be 2 times theta. Right? But there's going to be harder problems. There's going to be harder solutions that we're going to talk about next. Okay.
Oh, I don't get how you got x equals a sin theta.
To start off with.
Yeah.
Yep. So it's kind of like, how did we get that thing to do regular U-substitution? We recognize that that was the substitution we needed to make because we've practiced a lot of seeing that inside function whose derivative was a factor, right? So here, it's understanding these relationships that if I have that, if I have a number, if I have 1 minus x squared, if I replace the x with sine theta, I will be able to simplify it to just one item. If I have some number plus an x squared, if I get rid of the x and put in a tangent, I'll be able to use the simplification. So it's seeing these two things, saying, oh, okay, I can leverage this, taking 2 things and turning it into one thing, to think about what the best substitution would be. Once again, your book will say, if you see a squared minus x squared, then let x equal a sine theta. And if that works for you, by all means. This is kind of like the why behind those rules. I mean, I guess the why, why do we do that? Because it works. Right. The question is, can we see that it will work? So my problem, I had 4 minus x squared, and a squared minus x squared. The substitution is x equals a times sine theta. So it's the square root of this piece times sine theta. And once again, the reason is because look what happens when we plug it in. It just works. Okay. Other questions? It's complicated. So if you're feeling a little cloudy, that's okay. You go through and work some homework problems, and hopefully that will clarify. There is a video for this on my website again, because I was watching it. It's assuming you've had this lecture, right? And then it goes through a big example problem. So it might be something better to refer to after this if you're still stuck. And of course, YouTube's great, right? I mean, if you search trig substitution on YouTube, I am sure you'll find tons of videos with examples and whatnot. So that's another resource if you get stuck. All right. The biggest piece, though, is just what you said. It's identifying that right piece. So let's look at a couple and see if we can just practice that first step. It's not actually doing all the integrals, but look at each one of those and see if you can come up with the correct substitution. What would be a good substitution to use here? I'll say in general we do sine substitutions and tangent substitutions. You could probably be a little creative, use a cosine or a secant. Should probably still work as long as you follow the rules. But traditionally, sine and tangent are used. What about this first one? What do I want x to be in this first one? 3 sine theta. And if we don't worry about the derivative, we don't worry about placing dx, if we were to plug that in, we would get 9 minus x squared. When I square it, I get 9 sine squared theta. Factor out the 9, I will get 9 times 1 minus sine squared. I'll get 9 times cosine squared. Of course, the real process, we actually have to take the derivative and get rid of the dx piece as well, but this is just kind of identifying why that substitution works. What about the next one? X equals 4 times tangent of theta. When I plug that in the denominator, I'll get 1 over 16 plus this thing squared. 16 tangent squared theta. Factor out the 16 and I have 1 plus tangent squared, which is secant squared. Taking the two terms and condense it to one term. What about the next one? This one's a trick one. Oh, this one will be a U-substitution problem. It's one of those things, don't get married to a technique. Every section we're like, this is how we use this technique. You have to, in the back of your mind, remember that there's usually a process for these. You always look for U-substitution first because it's just easier. Here, I have x squared stuff, but I have an x in my numerator. That's going to help. So here I could let u equal 2 minus x squared and do regular U-substitution, not trig substitution. So a lot of these intervals are going to look very similar. So you don't want to get tied to it. Anytime I see the square root of a quadratic, I will use trig substitution. That might not be the best technique. It might still work here, but it is going to be harder, for sure. And then the last one. Last one's a little tricky because of that stupid 9. Right? I know how to deal with the some number squared minus x squared. I don't know how to deal with this weird 9 squared. So get rid of it. Factor that piece out. If I were to factor that piece out, it would look like the square root of 9 times some stuff. Factoring the 9 out. And then it's like a question, okay? 9 times what gets me to 4? 4/9. Okay? And then I would have minus x squared. Okay? So by factoring that 9 out here, I kind of put it into a form where I have something squared minus something squared. And now maybe I can see what that proper substitution is going to be. It's going to be 2/3 sine theta. Okay? So if we write that out here, x will equal 2/3 sine of theta. Here's my a squared. So that must be a. Because I have number squared minus x squared, I know it's a sine substitution. So that's going to be the substitution. Any questions about that? You don't have to. You could recognize it from the beginning. That'd be totally fine. I mean, because if you take this and you plug it into here, right, it's just going to get 4/9. The 9 is going to cancel with this 9, and you'll have 4 minus 4 sine squared theta. So it'll totally work. Right? I just factor it out so we can kind of see it more easily. It's more of a process to find out what that a value is. Okay? Other questions? Any questions? Okay. So, that's not all. It gets harder. So there's two other pieces that are going to make this a lot more challenging. One, we have this kind of weird quadratic form in here. And I need to write it like I write trig stuff, right? X squared minus some number squared. I can still do that, but to do that I have to complete the square under here. That will give me something like, x minus 2 squared plus 4. And I'll have that thing squared minus number squared or plus number squared. So I might have to complete the square under here. But as we go through this process, we're also going to see that the solution might come out weird. The solution might contain expressions that are hard to represent when we try to go back to our x's. Okay? So, we're going to start this thing. First step is going to be to complete that square. All right, so why don't you take a second and see how far you can get. So first step is complete the square. So you can even take this thing out separately, write it up here, go through that completing the square process. That's why we practiced it the other day. Remember, it's always not a quiz. If you get stuck, talk to your neighbor, figure out what that piece has to be. Remember, as you're working to look happy. I'm going to start my process and work through a little bit here. So I'm going to rewrite it into a kinder form for myself. I don't like having negatives up front. I'm sure you can work with them directly. It's just more comfortable for me. I factor out a negative sign. I write my quadratic in kind of a normal form here. And the idea is I have x squared minus 4x. But really I got to figure out what goes here. Now, what's the number that I wish was here so this would be a perfect square? How do I find that? Divide by 2 and square it. So I have 4 divided by 2 is 2. I square it, I get positive 4. So I really wish this was positive 4 here. But of course I need that value to be 3, so this is really 4 minus 1. There's my 1 kind of hanging out. Okay? Now the whole reason for doing that is because this piece is just x minus 2 quantity squared. And so now, if I just redistribute that negative sign, it's going to look like 1 minus x minus 2 quantity squared. Which is great, because now I have number squared minus thing squared. Right? It's x minus 2, but x, but we'll count for that. All right, so far I have x over the square root of 1 minus x minus 2 squared dx. And now I need to make my substitution. Now normally, I let x equals a, and if it was 1 minus something squared, it'd be sine theta. I wish this would turn into sine squared theta. So I'm going to let x minus 2 equal sine theta. So I'm going to let x minus 2 equal sine theta. it's kind of like helping me to get that right substitution. I could have started and said let x equal 2 plus sine theta. But writing is that x minus 2 equals sine theta kind of will help me to get to that step. So there's my substitution. Now we go through the process. I let x equal this. Now I take the derivative. So go ahead, take that derivative and plug all your stuff in, and we'll see what we get. See if you can finish the rest of the problem here. So the place our x's is what they're equal to. Take the derivative and put in the dx. See if we can do some simplification. Big lots of problem. Integrals, trig stuff. Bring some home to your parents. I love it. Get stuck, feel free to raise your hand or talk to your neighbor or do what it takes to get unstuck. Plugging in now. Replace x by what it was equal to. Replace the x minus 2 as sine. The derivative, I plug that piece in. Looks pretty ugly. But what do we have in the denominator? What is 1 minus sine squared? Cosine squared. What's the square root of cosine squared? So really this thing simplifies to this. And then my cosines cancel out. So I'm really just integrating 2 plus sine theta. What's the integral of 2? 2 theta. What's the integral of sine of theta? Negative cosine of theta. All right, piece of cake, right? And now I just got to plug in my x's again. So we have x minus 2 equals sine of theta. And the first thing I need to figure out what theta is. What is theta? Arc sine of x minus 2. Arc sine of x minus 2. And now I got to find out what cosine of theta is. What is cosine of theta? Well, technically speaking, we could say, well, cosine of theta should be the cosine of the arc sine of x minus 2. That doesn't really help us. There's some weird domain issues with those functions. Arc sine is only defined over a certain range. If we're trying to do cosine, things just get a little annoying. And there's a much better way we can represent this thing. But it's going to require us to go back to the trig triangle. right, so here's what I'm going to do. This is the expression I have. X minus 2 equals sine of theta. I'm going to draw myself a trig triangle. So it's a right triangle. I'm going to mark some angle equal to theta, whichever angle you want. Now, the sine and the cosine and the tangent all talk about the relationships inside this triangle, but they're all ratios. It's the ratio of sines. So I can scale this triangle however I want, really. It's the ratio that's important. So I'm going to pick a nice ratio. I'm going to pick a hypotenuse of 1. So it's like a unit right triangle. But I know that sine of theta equals x minus 2. Sine of theta is equal to the opposite side over the hypotenuse. So because I know that, this opposite side must have a length x minus 2. Because sine of theta has to equal this thing over this thing. Sine of theta is equal to this. So far, so good? But if I have two sides of a right triangle, I know what the third side is. How can I find the third side? Pythag, right? So whatever this side is, I'll call it b. Whatever that is, b squared plus x minus 2 squared better equal 1. And when I solve that for b turns out to be the square root of 1 minus x minus 2 squared. So now I know what the third side is. Now I know all three sides of my right triangle, which means I can figure out what cosine of theta is. Now I've defined this triangle fully. What is cosine of theta? Adjacent over the hypotenuse. Luckily our hypotenuse is 1, so it's easy to divide by 1. So cosine of theta then is this. It is the square root of 1 minus x minus 2 quantity squared. That's a much cleaner representation for cosine of theta than the arc, or than cosine of the arc sine of x minus 2. I only take cosines of arc sines. So this cosine of theta turns out to be the square root of 1 minus x minus 2 squared. All that stuff plus c becomes our antiderivative. Long process. Once again, remember those kind of key steps as you went along. We identified the right substitution. But even to get to that step, we had to complete the square. We complete the square. That helps identify the substitution. Mechanical, 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 integrate. Okay? But now going back to x's was kind of tricky. First one wasn't too bad, but I had to use the trig triangle for the other piece. And I can use my representation to define two sides. I can use Pythag to find the third side. And once I have all three sides, I can do whatever I want. I mean, maybe this integral turned out to be the tangent of something. Well, no problem. I know what tangent of theta is. It's the opposite over the adjacent. Taking also like this. Opposite of adjacent. Any questions? Yep.
Does it always turn out where that arc or the cosine of arc line is the same as what's on the bottom?
It's like, yeah, hey, didn't I see that thing before, right? It's right up there. I think some weird stuff can go in along the way. So I'd be a little nervous to generalize it like that. So you'd have to go through it and prove that to me.
Okay.
But if you can prove it to me, then your business. Since the book doesn't give us that as a shortcut, I'm guessing it fails somewhere. But it'd be interesting to look at. Good question. Other questions?
Should we always pick one as the hypotenuse?
Yes. I mean, you could make it more complicated, but make it more complicated. Any questions? All right, so now that we got that easy problem out of the way, there's no way we're going to have anywhere near the time to do this problem. So I'm going to sketch its solution really quick here in a couple minutes. We look at this and say, okay, it doesn't look too bad, right? X plus 1, x2 plus 4x. Not too bad. I look at it and say, well, I really can't simplify it I mean, maybe I can do a little bit. Let me factor the denominator. Maybe an x plus 1 will jump out. Nope. Not so lucky. Yeah. Maybe I can take the derivative. I don't know. It's weird terms again. It just looks hard. But I do have the ratio of polynomials, so I might think partial fractions might work. So I could do a partial fraction decomposition. I could do a over x plus bx plus c over x squared plus 4. Because I have one linear term and I have one irreducible quadratic. I have to go through the partial fractions to figure out what those constants are. But if I had the constants, well, then I'd have a times the natural log of the absolute value of x. And then how do I do this other piece again? What am I going to do with this thing? Maybe, I don't know if I can do that right away. I think I'd break this into two pieces first. Because if I write this like bx over x squared plus 4 plus c over x squared plus 4, I can do this one with just substitution. So that's actually what I would do. I would say plus the integral of bx times x squared plus 4 plus the integral of c over x squared plus 4 dx. And then I would do a U-Substitution on this one, and I would do a Trig Substitution on this one. And I go through the process, and it's a pretty long process. Questions? All right, so we went through quite a few problems. Like I said, that video on my webpage, we'll go through another complicated example where you're completing the square and doing a lot of trig stuff. The last thing I will say then is we have the big summary that just kind of summarizes what we did. We use this technique when we have quadratics that we want to get rid of, when we have roots of quadratics, or we have quadratics that don't have that x in the numerator where I can just use substitution. We use these two trig identities to really be the catalyst to help us choose which x to use, and then we just go through the process. For Monday, read through section 7.6 and 7.7. We'll go through 7.6 relatively quickly. 7.7 will be the focus. It's numerical techniques. We're going to do numerical integration. Start reviewing for exam 1. I'm going to try to get a practice exam sent out hopefully tomorrow. But don't wait. Exam is next Thursday. So this is the weekend before the exam. So start focusing on that, looking back at stuff. Yep.
Will we have a note card for the exam?
A note card. Oh boy, that was asked before. Yeah. I will send out a for sure answer to that by tomorrow. Okay. The other thing, try to work through the labs in advance. All right, there are 2 labs that have coming up. One I think is due on Tuesday of next week. One is due the following Friday. The one on Tuesday helps you work with tables. It's a setup for the next lab, which is having you program some of the numerical techniques. So those are the stuff we're going to talk about on Monday. So try to work on them a little bit ahead of time so you have time to ask questions, so you've seen some of the techniques. Those labs are here to support the course. So programming numerical techniques gives you a strong understanding of numerical techniques. And we're going to do some of that in class as well. So if nothing else, at least go through them, preview them a little bit, kind of read through them, even if you leave the work till later. All right, that's all I have. Office hours are right now.